Taylor method of order 4, but Taylor method of order 2 is definitely on the table, right? So make sure that you know how to be able to come up with the Taylor method of order 2. So let's write down a couple of the terms for the Taylor method of order 2 so that we know how to do it. So let's do that here. So erase this. Let me box these two guys as well. Taylor method of order 2. Taylor method of order 4. And by the way, of course, this approximation, the higher the order, the better the approximation is going to be, right? But you can notice that the higher the order, the more complicated the formula becomes, right? The more complicated the method becomes. Euler's method is the least complicated of the bunch, but its accuracy is low. Taylor method of order 2 is a good, kind of a good middle ground. It gives you much better accuracy, and it's not as complicated. We're going to be looking at Runge-Kutta formulas next, in which you get a lot better accuracy for the complication that you end up getting with Runge-Kutta. You gotta excuse that, right? That noise. That was my wife closing the curtains there. All right, so let's do this. All right. So erase this stuff here. Let's do an example. Okay. Say for our same one that we've already been doing, for y prime equal to, in this case we have y minus t squared plus 1. Our initial value problem, y of 0 is equal to 0.5. Approximate, let's just say y of 0.6 using the Taylor method. Of order 2. Okay. And we'll let our h be equal to 0.2. H equals 0.2. Alrighty then. Okay. We've already come up with the Taylor method of order 2. So let's just do what we can then, right? We're going to create our table. N, T sub n, Y sub n. We have n equals 0, 1, 2. I think 3 is what I need. So I have 0, 0 0.2, 0 0.4, 0 0.6. Okay. And I want to be able to calculate the y values here, right? So I need to calculate 3 y values. Because I already given y sub 0. Y sub 0 is equal to 0.5. Okay. So let's plug it in, see what we get. So we do the first one. We have y sub 1. Okay. Using this formula here. That is equal to y sub 0 plus y sub 0 minus t sub 0 squared plus 1 times 0.2 plus, oh my goodness, this is big, right? Plus. The next term is y sub 0 minus t sub 0 squared minus 2 t sub 0 plus 1 times 0.2 squared over 2. So let's see what we get there. Do that. Okay, plugging in. We get y sub 1 is equal to y sub 0, which is 0.5, plus 0.5 minus t sub 0, which is 0, plus 1 t sub 0 squared, times 0.2, plus 0.5 minus 0 squared, minus 0, 2 times 0, which I don't really need to write, plus 1 times 0.2 squared divided by 2. If you work this out, I think you get about 0.83. Again, this is in the book, in the table, 0.83. Let's plug in y sub 2. Y sub 2. Put it here. And let's kind of skip that middle step there, y sub 2. So I'm going to skip this step, which is going to be equal to y sub 1. Y sub 1 is going to be 0.83 plus the quantity 0.83 minus, in that case it's going to be t sub 1. T sub 1 squared, which is going to be 0.2 squared plus 1. I can look at this guy here too, times 0.2 plus, and you guys probably can't see that, so I'm going to come down here, plus, we go to the next one, y sub 1, which is going to be 0.83 minus 0.2 squared minus 2 times 0.2 plus 1 times 0.2 squared over 2. And if you do that one, what do you get? They have 1.215. 1.215. 1.215. 1.215.8. Okay. I'll give them as many decimal places they have. 1.2158. Okay. And let's do one more. Y sub 3. I'll do it. I can put it right underneath y sub 3, right here. Got the bin down low to see it. Y sub 3 is going to be 1.2158. I'll keep wanting to switch that around. Plus the quantity, y sub n, so that'll be y sub 2 that we're using, which is going to be 1.218215.8, oh my goodness, minus t sub n, so that's going to be t sub 2. T sub 2 is 0.4 squared plus 1 times 0.2 plus, this is a good thing for your calculator to kind of make a little program for, right? You can store a couple of variables, and then we can use the formula just to enter to get like the next term in the method, similar to what we did with the secant and Newton's method. And then this would be 1.2158 minus 0.4 squared minus 2 times 0.4 plus 1 times the quantity 0.2 squared divided by 2. Okay. And for that one, they get 1.652. 1.652 to what? To essentially 2.1. Keeping it to 4 decimal places. 1.6521. Which is not a bad at all approximation. If you compare these values that you have here, if you compare these values that you have here with the actual solution at those places, the approximation is really pretty good in each one of those instances. Okay, and the absolute error, so much better than Euler's method when we use this. Of course, you can do the same thing for the Taylor method of order 4, right? But you can notice that was going to take even longer for us to plug it in, right? This is where a Excel or a calculator or computer programming this would be much more beneficial to use in this case. Like I said before, on a test or in the homework, you guys are going to be responsible for Taylor method of order 2 and of order and of Euler's method when you approximate a differential equation. All right, so that's it for this particular lesson, and we'll stop and pick up later with Runge Kutta.